You think you understand the universe? Particles have mass, particles have location, particles follow rules, but the quantum world laughs at what you think you know. There are particles that exist in two places at once. Particles that pop into existence from nothing. Particles that are their own antiparticles. Particles that exist only on surfaces. Particles that carry fractional charges. And just this year, in January 2025, researchers found particles that break every category we thought we had. The quantum realm is weirder than your brain wants to accept. Every solid thing around you, built from pieces you cannot see. Pieces smaller than atoms. Pieces smaller than protons. Pieces that obey laws so strange that even Einstein called them spooky. These are quantum particles, and they come in flavors that defy imagination. If you value documented quantum physics and cutting-edge particle research like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from Brown University's Nature publication dated January 8, 2025, announcing fractional excitons, and Purdue University's research from February 21, 2024 on 6 flux composite fermions published in Nature, and verified through multiple peer-reviewed physics journals. Now back to the information. 17 particles form the foundation of everything you can touch, see, or measure. 17 particles in the Standard Model, confirmed through decades of experimental physics, govern every interaction in your body and the farthest galaxy. But that number deceives you. The quantum world contains far more than 17. It contains particles nobody predicted, particles that shouldn't exist according to the mathematics we wrote in the 1960s and 1970s. Particles found only this decade. The Standard Model divides particles into 2 families. Fermions build matter. Bosons carry forces. 12 fermions exist as the construction blocks of atoms, stars, and human tissue. 5 bosons mediate the electromagnetic force, the strong nuclear force, the weak nuclear force, and mass itself. Clean categories, simple divisions. Wrong picture. The universe has other plans. Start with fermions. These particles possess half-integer spin, either 1/2 or 3/2. They obey the Pauli exclusion principle, which means no 2 fermions can occupy the same quantum state at once. This single rule creates solid matter. Electrons cannot pile into identical states, so they stack in shells around atomic nuclei. Shells create chemistry. Chemistry creates molecules. Molecules create you. Fermions make structure possible. 6 quarks and 6 leptons comprise the 12 fermions. Quarks combine in groups of 3 to form protons and neutrons. The up quark and down quark populate every atom in your body. The up quark carries positive 2/3 charge. The down quark carries negative 1/3 charge. 2 ups and 1 down make a proton with charge, positive 1. 1 up and 2 downs make a neutron with charge 0. Simple arithmetic from fractional charges. Quarks never exist alone. The strong force binds them so tightly that isolating one requires infinite energy. Try to pull quarks apart and you pump in so much energy that new quarks pop from the vacuum instead. 4 other quarks exist, heavier and stranger. The charm quark and strange quark form the 2nd generation. The top quark and bottom quark form the 3rd generation. The top quark holds the record as the heaviest elementary particle, weighing 173 billion electron volts, roughly the mass of a gold atom compressed into a point. It decays in 5 × 10 to the negative 25 seconds. You need particle colliders to create top quarks. They vanish before they can form bound states. 6 leptons partner with the quarks. 3 charged leptons, electron, muon, tau. 3 neutral leptons, electron neutrino, muon neutrino, tau neutrino. Electrons orbit atomic nuclei and flow through wires as electricity. Muons and taus are heavier copies of the electron. The muon decays in 2 microseconds. The tau decays in 3 × 10 to the negative 13 seconds. Only electrons remain stable. Neutrinos pass through matter like ghosts. 100 trillion neutrinos from the sun pierce your body every second. Most pass through Earth without hitting a single atom. Neutrinos have tiny masses, less than 1/millionth the mass of an electron. Nobody knows the exact mass. Neutrinos oscillate between 3 flavors as they travel, switching from electron neutrino to muon neutrino to tau neutrino and back. This oscillation, confirmed in 1998 by the Super Kamiokande detector in Japan, proved neutrinos possess mass. Bosons carry forces. 5 known bosons mediate interactions. The photon carries electromagnetism, massless, travels at light speed, mediates every interaction between charged particles. Radio waves, visible light, X-rays, gamma rays, all are photons at different energies. 8 gluons carry the strong force. They bind quarks inside protons and neutrons. Gluons themselves carry color charge, so they interact with each other, creating a force that grows stronger at distance. The W plus W minus E and Z bosons carry the weak force. These particles have mass 80 and 91 gigaelectronvolts, respectively. The weak force causes radioactive decay. A neutron decays by emitting a W minus boson, which splits into an electron antineutrino. The Higgs boson completes the Standard Model. Discovered July 4, 2012 at CERN's Large Hadron Collider near Geneva, Switzerland. The ATLAS experiment and CMS experiment independently detected a new particle at 125 gigaelectronvolts. Both collaborations reached 5 sigma significance, meaning the probability of a false signal was less than 1 in 3 million. Fabiola Giannotti, spokesperson for ATLAS, and Joe Incandela, spokesperson for CMS, announced the discovery to a packed auditorium. Peter Higgs and Francois Englert, who predicted the particle in 1964, received the Nobel Prize in Physics the following year in 2013. The Higgs boson emerges from the Higgs field, an invisible field filling all space. Particles gain mass by interacting with this field. The stronger the interaction, the greater the mass. Photons and gluons ignore the Higgs field and remain massless. Electrons, quarks, and W and Z bosons interact with the field and acquire mass. The Higgs mechanism explains why some forces act at long range and others confine to atomic nuclei. The Higgs boson has 0 spin, making it the only fundamental scalar particle in the Standard Model. That covers 17, but the quantum world contains far stranger particles. Particles that exist only in 2 dimensions. Particles that swap quantum states by braiding around each other. Particles with fractional statistics. These are quasiparticles and emergent particles, not fundamental like electrons or quarks, but arising from collective behavior in materials. Anyones exist only in 2-dimensional systems. In 3 dimensions, only fermions and bosons are possible. Exchange 2 identical fermions, and the quantum wave function picks up a minus sign. Exchange 2 identical bosons, and nothing changes. These are the only options in 3 dimensions, but 2 dimensions allow a third option. Exchange 2 anyones, and the wave function picks up any phase factor between 0 and 2 pi. Hence the name anyone, coined by Frank Wilczek in 1982. John Magna-Linus and Jan Meyerheim showed in 1977 that the fermion-boson dichotomy breaks down in 2 dimensions. Anyons divide into abelian and non-abelian. Abelian anyons were detected in 2020 in fractional quantum Hall experiments. Apply a strong magnetic field to a 2-dimensional electron gas at near absolute 0 temperatures, and the electrons form exotic states. The Hall conductance jumps in fractional steps, not integer steps. These fractional states host quasiparticles with fractional charge, an experiment by researchers at Purdue University. Published in Nature Physics in September 2020, measured anyonic braiding directly. They created a device where quasiparticles with 1/3 electron charge flowed in paths that looped around standing quasiparticles. When the looping quasiparticles completed a circuit, the interference pattern jumped by a phase of 1/3. Direct proof of anyonic statistics. Non-abelian anyons are even stranger. Braiding non-abelian anyons changes not just the phase, but the quantum state itself. The final state depends on the order of braiding operations. Non-abelian anyons form the basis for topological quantum computing. Proposed by Alexei Kitaev in 1997. A topological quantum computer stores information in the braiding patterns of anyons. These patterns are topologically protected, meaning local perturbations cannot corrupt them. You would need to unravel the entire braid to introduce errors. This makes topological qubits incredibly stable compared to conventional qubits. The challenge is finding materials that host non-abelian anyons. The best candidate is the fractional quantum Hall state at filling fraction 5/2, discovered in GeS heterostructures at magnetic fields around 5 Tesla and temperatures below 1 Kelvin. Experiments suggest this state contains icing anyons, but definitive proof remains elusive as of 2025. Just this year, January 8, 2025, Anders. Brown University researchers discovered an entirely new class of quantum particles, fractional excitons, published in Nature. The team included Jia Li, Nayuan Zhang, Ron Nguyen, Navketan Batra, and Dima Feldman. They built a device with 2 atomically thin layers of graphene, separated by hexagonal boron nitride. They applied magnetic fields millions of times stronger than Earth's field. Inside this device, electrons paired with holes, the absence of electrons, to form excitons. But these were not ordinary excitons. These excitons carried fractional charge. They behaved like neither bosons nor fermions. They showed properties of both, like anyons, but distinct from anyons. The fractional excitons arose from the fractional quantum Hall regime. Electrons in this regime form composite fermions by capturing magnetic flux quanta. Normally, composite fermions capture 2 or 4 flux quanta, but Zhang, Nguyen, and Batra observed composite fermions capturing 6 flux quanta. 6 flux composite fermions, reported by Purdue researchers in February 2024. These create fractional excitons when paired with holes. Jolly stated the fractional excitons represent an entirely new class of quantum particles following unique quantum statistics. They carry no overall charge, but defy the standard fermion boson division. Whale fermions were predicted in 1929 by Hermann Weyl, but not observed as elementary particles. Neutrinos looked like whale fermions for decades. Massless, spin 1/2 particles with definite chirality. But in 1998, neutrino oscillations proved neutrinos have mass, ruling them out as whale fermions. The particle physics community moved on. Then, in 2015, 3 independent teams found whale fermions in crystals. Not elementary particles, but quasiparticles in topological semimetals. One team discovered them in tantalum arsenide in July 2015. Another team found them in different tantalum arsenide samples in August 2015. A third team predicted them in photonic crystals in 2015. After 85 years, whale fermions emerged not from particle accelerators, but from solid-state physics. Whale fermions in crystals are massless and travel at speeds determined by the crystal structure. They cannot scatter backward. They carry charge with almost no resistance. In tantalum arsenide, whale electrons move 1,000 times faster than electrons in conventional semiconductors, twice as fast as in graphene. The speed comes from their topological protection. The crystal structure forbids certain scattering processes. Type 2. Whale fermions arrived in November 2015. Alexei Solyanov and collaborators predicted them in tungsten diteluride. These particles break Lorentz symmetry. Impossible in high-energy physics, but allowed in condensed matter. Type 1. Whale points have point-like Fermi surfaces. Type 2. Whale points appear at contacts between electron pockets and hole pockets. The Fermi surface tilts over, creating exotic transport properties. Experiments confirmed type 2 whale fermions in materials like WTE2 and MOTE2. 3-component fermions defy the standard classification. Dirac fermions have 4-fold degeneracy. Whale fermions have 2-fold degeneracy. Researchers at the Chinese Academy of Sciences and collaborators discovered 3-component fermions in molybdenum phosphide in June 2017, published in Nature. The crystal structure creates triple points where 3 bands meet. Quasiparticles near these points exhibit 3-fold degeneracy. They sit conceptually between Dirac and whale fermions. The material also hosts standard whale points elsewhere in its band structure, allowing study of how different fermion types coexist. Majorana fermions are their own antiparticles. Ettore Majorana predicted them in 1937. Every other fermion has a distinct antiparticle. Electrons have positrons. Quarks have antiquarks. Majorana fermions are particles that equal their own antiparticles. Neutrinos might be Majorana fermions. Experiments search for neutrinoless double beta decay, where a nucleus emits 2 electrons with no neutrinos, requiring neutrinos to be their own antiparticles. Results remain inconclusive. In condensed matter, Majorana zero modes appear as excitations in topological superconductors. A team led by Leo Kouwenhoven published evidence in Nature in 2018, but retracted the paper in 2021 after further analysis showed the signal could arise from other effects. As of 2025, no conclusive experimental confirmation of Majorana fermions exists, though multiple groups continue searching in superconductor nanowire devices and fractional quantum Hall systems. Composite fermions explain the fractional quantum Hall effect, discovered by Dan Suey, Horst Stormer, and Arthur Gossard in 1982. They applied strong magnetic fields to 2-dimensional electron gases at temperatures near absolute zero. The Hall resistance showed plateaus at fractional values, 1/3, 2/5, 3/7. Jainendra Jain proposed in 1989 that electrons capture magnetic flux quanta to form composite fermions. Each electron binds with 2 flux quanta, becoming a composite fermion with charge -1 and effective mass different from an electron. These composite fermions then fill Landau levels just like electrons in a weaker effective field. The fractional quantum Hall states emerge from integer quantum Hall states of composite fermions. The theory explained over 90 observed fractional states. In February 2024, Gabor Sathi and collaborators at Purdue discovered 6 flux composite fermions, where electrons capture 6 flux quanta instead of 2 or 4. published in Nature, that is Psi. They measured fractional states at filling fractions 2/11 and 3/17. The numerology revealed 6 flux, 2/11 equals 2 divided by 2 times 6 minus 1. 6 flux composite fermions create the most intricate composite fermion known. This discovery expanded the periodic table of fractional quantum Hall states. Dark excitons hide from light. Excitons are bound pairs of electrons and holes in semiconductors. When an electron and hole recombine, they typically emit light. Dark excitons cannot emit light due to selection rules. Their spin configuration forbids radiative decay. Scientists at Okinawa Institute of Science and Technology tracked dark excitons in October 2025 using magnetic fields and strain. Dark excitons live longer than bright excitons because they cannot decay by photon emission. This stability makes them candidates for quantum information storage. The OIST team published their methods for controlling dark excitons in atomically thin materials. Phonons are quantized sound waves. Lattice vibrations in crystals behave as particles with quantized energy. Phonons carry momentum and interact with electrons. They mediate superconductivity in conventional superconductors. Electrons pair into Cooper pairs by exchanging phonons. The phonon interaction overcomes electron-electron repulsion at low temperatures, allowing formation of a superconducting condensate. Phonons also carry heat. Thermal conductivity in insulators arises entirely from phonon transport. In 2025, researchers at University of Chicago demonstrated high-fidelity entanglement between acoustic wave resonators, quantum sound, published in Nature Communications. Andrew Cleland's group showed that macroscopic mechanical oscillators can exhibit quantum entanglement, opening applications in quantum sensing and communication. Magnons are quantized spin waves in magnetic materials. Flip one spin in a ferromagnet, and the disturbance propagates as a wave. These waves are magnons. They carry angular momentum but no charge. Magnons mediate spin transport in insulators, enabling spintronics without electrical currents. Researchers use magnons to build low-power logic devices and quantum information processors. Magnon-based quantum computing proposals emerged in the last decade. Utilizing the long coherence times of spin waves in yttrium iron garnet and other magnetic insulators. Plasmons are collective oscillations of free electrons. In metals, conduction electrons can oscillate coherently in response to electromagnetic fields. These oscillations are plasmons. Plasmons in nanostructures create intense electromagnetic fields at sub-wavelength scales. Surface plasmons on metal nanoparticles enhance Raman scattering by factors exceeding 1 million, enabling single-molecule detection. Plasmons drive metamaterials with negative refractive index and cloaking devices. In graphene, plasmons reach terahertz and infrared frequencies with strong confinement, useful for optoelectronics and photodetectors. Polaritons hybridize photons and matter excitations. When photons couple strongly to excitons in semiconductors, the eigenstates become exciton polaritons, part light, part matter. These quasiparticles behave as bosons and can form Bose-Einstein condensates at temperatures far higher than atomic gases. Exciton-polariton condensates were demonstrated in CDT microcavities in 2006 and in gas in 2007. The condensates exhibit superfluidity, quantized vortices, and coherence. Polaritons enable low-threshold lasers and all optical logic. Polarons are electrons dressed by phonons. An electron moving through a crystal polarizes the lattice, creating a cloud of phonons around it. The electron plus phonon cloud forms a polaron with effective mass larger than the bare electron mass. Polarons mediate charge transport in organic semiconductors and metal oxides. In materials like titanium dioxide and zinc oxide, polarons determine conductivity and optical absorption. Large polarons spread over many lattice sites. Small polarons localize to single sites and hop between sites. Polaron formation explains the mobility of charge carriers in diverse materials. Rotons are excitations in superfluid helium-4. At temperatures below 2.17 Kelvin, helium-4 becomes a superfluid with zero viscosity. The excitation spectrum has a local minimum at finite momentum called the roton minimum. Rotons are quasiparticles near this minimum. Their origin puzzled physicists for decades. Neutron scattering experiments mapped the roton spectrum in detail. Rotons contribute to the specific heat of superfluid helium and limit superfluidity at higher temperatures. Recent theories connect rotons to density fluctuations and crystal-like ordering tendencies in the superfluid. Skyrmions are topologically stable spin textures. In magnetic materials, spins can wind into knot-like configurations that cannot unwind without cutting through other spins. Alexei Bogdanov and Anatoly Yablonsky predicted skyrmions in magnets in 1989. Christian Fleiderer's group discovered them in manganese silicon in 2009 using neutron scattering. Skyrmions are typically nanometers across and can be moved with tiny electrical currents. They exhibit emergent electrodynamics, acting like charged particles in applied fields. Skyrmions enable racetrack memory, where bits are stored as skyrmions in magnetic nanowires and shuttled past read-write heads. IBM and others are developing skyrmion-based memory with densities exceeding conventional hard drives and speeds approaching DRAM. Fractional charges defy intuition. Quarks carry charges of plus or minus 2/3 and plus or minus 1/3, never observed as free particles. But in the fractional quantum Hall effect, quasiparticles carry exact fractional multiples of the electron charge. The quasiparticles at filling 1/3 carry charge negative 1/3, at filling 2/5. Charge negative 2/5, at filling 5/2, the particles carrying charge negative 1/4 and negative 1/2 may be non-abelian anyones. Robert Laughlin explained the 1/3 state in 1983 with a many-body wave function. Laughlin's theory won the Nobel Prize in 1998, shared with Swee and Stormer. Fractional charges emerge from strong correlations among electrons in 2 dimensions and magnetic fields. No single electron carries fractional charge. The fraction appears only as a collective property of the many-electron state. Time crystals break time translation symmetry. Ordinary crystals break space translation symmetry by forming periodic structures. Frank Wilczek proposed in 2012 that phases of matter could break time translation symmetry, creating structures that repeat in time. Initial proposals faced no-go theorems, but in 2016, researchers realized time crystals could exist in driven, non-equilibrium systems. Experimentalists created time crystals in chains of trapped ions in 2017. Mikhail Lukin's group at Harvard and Christopher Monroe's group at University of Maryland independently observed time crystalline order. The systems exhibit subharmonic response, oscillating at half the driving frequency. Time crystals never reach equilibrium and retain coherence indefinitely in the driven, steady state. Applications to quantum memory and metrology are under investigation. Solitons are localized waves that propagate without dispersing. In certain nonlinear systems, dispersion and nonlinearity balance to create stable pulses. John Scott Russell observed solitary waves in a canal in 1834. The mathematical theory developed through the 19th and 20th centuries. Solitons appear in diverse contexts. Optical solitons propagate through optical fibers over thousands of kilometers without distortion, enabling long-distance telecommunications. Topological solitons, like magnetic domain walls, separate regions of different order. Solitons in Bose-Einstein condensates include dark solitons, density dips that move through the condensate. Josephson vortices in superconductors are solitons carrying single flux quanta. Cooper pairs enable superconductivity. Leon Cooper showed in 1956 that electrons in metals can pair via attractive phonon-mediated interactions. 2 electrons with opposite spins and momenta form a Cooper pair with lower energy than independent electrons. At temperatures below the superconducting transition, Cooper pairs condense into a macroscopic quantum state. The pairs move through the lattice without resistance. Breaking a Cooper pair requires a minimum energy, the superconducting gap. BCS theory, developed by John Bardeen, Leon Cooper, and Robert Schrieffer in 1957, explained unconventional superconductors, high-temperature superconductors, discovered in 1986, involve more complex pairing mechanisms not fully understood. Quantum Hall edge, states carry current without dissipation. In the quantum Hall effect, bulk states are gapped, but edge states remain gapless. Current flows only along the edges of the sample. These edge states are topologically protected. Backscattering requires interidge scattering across the sample width, suppressed exponentially for wide samples. Edge transport in quantum Hall systems is quantized with precision exceeding 1 part in 10 billion. The quantized Hall resistance defines the modern standard for resistance. Integer quantum Hall edge states are chiral, propagating in one direction only. Fractional quantum Hall edge states can support both forward and backward propagating modes, depending on filling fraction and interaction strength. Entangled particles defy locality. When 2 particles are entangled, measuring one instantly affects the other, regardless of distance. Einstein, Podolsky, and Rosen highlighted this in 1935, calling it spooky action at a distance. John Bell formulated testable inequalities in 1964. Experiments by Alain Aspect in 1982 and many others since have violated Bell inequalities, confirming quantum entanglement. Entanglement enables quantum teleportation, where quantum states transfer between particles without physical transmission. Anton Zeilinger's group demonstrated teleportation over 143 kilometers in 2012. Entanglement is the resource for quantum computing, quantum cryptography, and quantum sensing. Creating and maintaining entanglement remains a central challenge in quantum technology. Virtual particles arise from quantum fluctuations. The uncertainty principle allows energy conservation violations over short timescales. Particle-antiparticle pairs pop into existence and annihilate within intervals set by their mass. These are virtual particles. They mediate forces. Photons exchanged between charged particles are virtual. Gluons binding quarks are virtual. W and Z bosons in weak decays are virtual. Virtual particles cause the Casimir effect, where uncharged parallel plates in vacuum attract due to modified vacuum fluctuations between them. Hendrik Casimir predicted this in 1948. Experiments confirmed it in 1997. Virtual particles contribute to the electron's magnetic moment with precision matching theory to 10 significant figures. Gravitons remain hypothetical. Quantum field theory predicts that gravitational waves should be quantized as gravitons. Massless spin 2 bosons, but gravity is exceptionally weak at quantum scales. Detecting individual gravitons is far beyond current technology. The gravitational interaction between 2 electrons is 10 to the negative 43 times weaker than their electromagnetic interaction. LIGO detected gravitational waves from black hole mergers in 2015. Confirming gravity propagates as waves at light speed. But quantizing gravity remains the deepest problem in theoretical physics. String theory, loop quantum gravity, and other approaches attempt to reconcile general relativity and quantum mechanics. None have experimental verification. Axions are hypothetical particles proposed to solve the strong CP problem in quantum chromodynamics. Roberto Pache and Helen Quinn introduced the mechanism in 1977. Axions would be very light, possibly 1/1,000,000th of an electron volt or less. They interact extremely weakly with ordinary matter. Axions are a leading dark matter candidate. The Axion dark matter experiment at the University of Washington searches for axions by looking for their conversion to photons in strong magnetic fields. Similar experiments operate worldwide. No confirmed detection as of 2025X, but the parameter space narrows. Axion detection would solve 2 mysteries: the strong CP problem and the nature of dark matter. Sterile neutrinos might exist beyond the 3 known neutrino flavors. Anomalies in neutrino experiments hint at additional neutrino states that do not interact via weak force, hence sterile. These would be right-handed neutrinos or heavier partners of the known neutrinos. The mini-Boon A experiment at Fermilab observed an excess of events consistent with a 4th neutrino with mass around 1 electron volt. Other experiments give conflicting results. The sterile neutrino search at Fermilab aims to clarify the situation. Sterile neutrinos could explain dark matter if they have keV scale masses. X-ray observations of galaxy clusters show hints of a line at 3.5 keV that could be sterile neutrino decay. But other astrophysical explanations remain possible. Supersymmetric particles emerge from supersymmetry, a proposed extension of the Standard Model. Every fermion would have a bosonic superpartner. Every boson would have a fermionic superpartner. Electrons have selectrons. Quarks have squarks. Photons have photinos. Gluons have gluinos. The Higgs has Higgsinos. Supersymmetry predicts the unification of forces at high energy and provides dark matter candidates. The Large Hadron Collider has searched for supersymmetric particles since 2010. No evidence found. Lower bounds on sparticle masses now exceed 1 to 2 TeV for most scenarios. Supersymmetry may exist at higher energies beyond current reach, or it may not describe nature. Tachyons would travel faster than light. Special relativity allows solutions to the energy-momentum relation with imaginary mass. These are tachyons. They would move faster as they lose energy. Detecting tachyons traveling backward in time would violate causality. No experimental evidence for tachyons exists. They appear in early string theory formulations, but are regarded as instabilities, not physical particles. If tachyons existed, they would cause vacuum decay, making them incompatible with a stable universe. Magnetic monopoles are isolated north or south poles. Maxwell's equations contain no magnetic charge, only dipoles. Paul Dirac showed in 1931 that a single magnetic monopole would explain charge quantization. Grand unified theories predict monopoles formed in the early universe. Blas Cabrera reported a single event consistent with a monopole in 1982, never reproduced. Searches continue in cosmic rays, particle accelerators, and ancient minerals. Monopoles would have dramatic implications for particle physics and cosmology. Their absence remains puzzling. Quantum particles obey statistics more bizarre than classical probability. Identical particles in quantum mechanics are truly indistinguishable. Swapping two electrons does not create a new state. It either leaves the state unchanged for bosons or flips the sign for fermions. This leads to bunching for bosons and anti-bunching for fermions. Bosons cluster together. Multiple bosons occupy the same state in lasers, Bose-Einstein condensates, and superfluids. Fermions avoid each other, filling states one at a time. This creates the periodic table, stellar structure, and the stability of matter. Anyons in two dimensions interpolate between these extremes, creating new possibilities for quantum information. Quantum fields permeate space. Particles are excitations of quantum fields. The electron field exists everywhere. An electron is a ripple in that field. The photon field produces light. The Higgs field gives mass. Every interaction between particles is an interaction between fields. Virtual particles mediate these interactions. Quantum field theory combines quantum mechanics with special relativity. It is the most accurate physical theory ever constructed. Predictions match experiments to 15 decimal places for some quantities. Quantum electrodynamics, the theory of electrons and photons, was developed in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga. Quantum chromodynamics, the theory of quarks and gluons, solidified in the 1970s. The electroweak theory unifying electromagnetism and weak force earned Sheldon Glashow, Abdus Salam, and Steven Weinberg the Nobel Prize in 1979. The vacuum is not empty. Quantum fields fluctuate even at zero temperature. These fluctuations have measurable effects. The Lamb shift splits energy levels in hydrogen by parts per million due to virtual photons. The anomalous magnetic moment of the electron arises from virtual particle loops. The vacuum energy density contributes to the cosmological constant, though the predicted value exceeds observations by 120 orders of magnitude, the worst prediction in physics. Understanding vacuum energy remains a central mystery. Quantum entanglement extends beyond particle pairs. Many-body entanglement in materials creates topological order. Topological phases cannot be characterized by local order parameters. They require examining global properties of the wave function. Topological insulators have insulating bulk, but conducting surface states protected by topology, discovered in bismuth antimony in 2008. Topological superconductors host Majorana zero modes at defects and edges. Topological semimetals have protected band crossings, creating robust metallic states. These materials are platforms for quantum information and low-power electronics. Quantum phase transitions occur at zero temperature driven by quantum fluctuations rather than thermal fluctuations. Tuning a parameter like magnetic field or pressure can drive a system from one quantum phase to another. The transition point is a quantum critical point. Near quantum criticality, unusual physics emerges. High-temperature superconductors sit near quantum critical points in their phase diagrams. Understanding quantum criticality may unlock the mechanism for high-temperature superconductivity. Quantum computers harness superposition and entanglement to perform calculations impossible for classical computers. Shor's algorithm factors large numbers exponentially faster than known classical algorithms, threatening RSA encryption. Grover's algorithm searches unsorted databases quadratically faster. Quantum simulators model quantum systems that classical computers cannot handle. Google's Sycamore processor achieved quantum supremacy in 2019, performing a specific task in 200 seconds that would take classical supercomputers 10,000 years. IBM, Honeywell, IonQ, Rigetti, and others build competing platforms. Error correction remains the key challenge. Topological quantum computing with anyons promises intrinsic error protection. If non-abelian anyons can be controlled, quantum sensors exploit entanglement and superposition for precision measurement. Atomic clocks use quantum transitions to define the second with 18-digit precision. LIGO uses quantum squeezing to reduce noise below the standard quantum limit, enhancing gravitational wave sensitivity. Quantum magnetometers based on nitrogen vacancy centers in diamond detect magnetic fields at the femtotesla level, enabling medical imaging of brain signals. Quantum radar and quantum lidar are under development for enhanced detection and ranging. The January 2025 discovery of fractional excitons opened new territory. These particles do not fit into the Dirac-Weyl-Majorana classification. They are not bosons, they are not fermions, they are not standard anyons. They represent a fourth category, or perhaps a bridge between categories. Dima Feldman, co-author on the Brown paper, stated they have their finger on the knob of quantum mechanics, an aspect previously unknown or unappreciated. The implications are profound. Quantum computing could exploit fractional excitons for enhanced coherence. Quantum materials could host entirely new phases of matter. The Standard Model remains incomplete, describing only a fraction of the universe's particles. Dark matter comprises 85% of matter in the universe, yet none of the Standard Model particles are dark matter. Observations of galaxy rotation curves, gravitational lensing, and cosmic microwave background anisotropies require additional mass not accounted for by visible matter. Weakly interacting massive particles, or WIMPs, are a leading candidate. Experiments bury detectors deep underground to shield from cosmic rays and wait for WIMPs to scatter off nuclei. The Lux Zeppelin experiment in South Dakota sets the strongest limits as of 2025. No detection yet. Axions are another candidate. Ultralight dark matter composed of axion fields would behave as waves on galactic scales. Primordial black holes formed in the early universe could constitute dark matter, though constraints from microlensing and other observations limit their contribution. Dark energy drives the accelerated expansion of the universe, discovered in 1998 by observations of distant supernovae. It comprises 68% of the universe's energy density. Its nature is unknown. The cosmological constant, a constant energy density filling space, fits observations but lacks theoretical understanding. Quintessence. A dynamical field with negative pressure is an alternative. Modified gravity theories attempt to explain acceleration without dark energy. Recent proposals link dark energy to ultralight axion particles evolving over cosmic time. Observations of dark energy evolution would distinguish among models. Neutrino masses are not explained by the Standard Model. The Standard Model assumes neutrinos are massless. Neutrino oscillations require mass, but the mechanism is unknown. Direct mass terms require right-handed neutrinos not observed. Majorana mass terms violate lepton number, allowing neutrinoless double beta decay. The seesaw mechanism postulates heavy right-handed neutrinos that generate tiny left-handed neutrino masses via the Higgs mechanism. Experiments search for neutrinoless double beta decay in germanium, xenon, and other isotopes. The Gerda, EXO, and Camland. Zen experiments constrain neutrino masses and Majorana nature. Upcoming experiments aim for ton-scale detectors with sensitivity to neutrino masses below 50 millielectron volts. Baryon asymmetry puzzles cosmology. The universe contains matter with negligible antimatter. The Big Bang should have produced equal matter and antimatter. They should have annihilated, leaving only photons. Yet we exist. Andrei Sakharov outlined 3 conditions for generating baryon asymmetry in 1967. Baryon number violation, C and CP violation, and departure from thermal equilibrium. The Standard Model provides CP violation through the weak force, but the magnitude is insufficient. Leptogenesis proposes that heavy Majorana neutrinos decay with CP violation, creating lepton asymmetry that converts to baryon asymmetry through Sphaleron processes. Experiments measure CP violation in neutrino oscillations and meson decays to constrain models. Grand unification proposes that electromagnetic, weak, and strong forces merge at high energy. The running of coupling constants suggests they converge around 10 to the 16 gigaelectron volts in supersymmetric extensions. Grand unified theories predict proton decay with lifetime around 10 to the 34 years. The Super Kamiokande detector observes protons for decay signatures. None found. Proton lifetime exceeds 10 to the 34 years. This constrains or rules out many grand unified models. Magnetic monopoles and proton decay remain unfulfilled predictions. String theory posits that fundamental particles are not points, but one-dimensional strings. Different vibration modes correspond to different particles. String theory requires 10 or 11 space-time dimensions. Extra dimensions are compactified at scales around the Planck length, 10 to the negative 35 meters. String theory unifies gravity with other forces and avoids infinities plaguing point particle quantum gravity. But it makes few testable predictions. The landscape of string vacua may contain 10 to the 500 solutions, leading to the anthropic principle to explain our universe's parameters. Critics argue string theory is not falsifiable. Proponents argue it is the only consistent quantum gravity theory developed. Loop quantum gravity quantizes space-time itself. Space-time is woven from discrete loops and spin networks at the Planck scale. General relativity emerges as a low energy limit. Loop quantum gravity is background independent, requiring no fixed space-time structure. It predicts that singularities in black holes and the Big Bang are resolved by quantum effects. Observable predictions include possible deviations in the speed of light for high-energy photons due to granular space-time structure. Observations of gamma-ray bursts constrain or rule out some loop quantum gravity models. The Planck scale on a watt, 10 to the negative 35 meters and 10 to the negative 43 seconds marks where quantum gravity becomes essential. At these scales, space-time fluctuations dominate. Particle energies reach 10 to the 19 gigaelectron volts. The Planck energy. No experiment approaches these scales. The Large Hadron Collider reaches energies around 10 to the 4 gigaelectron volts, 15 orders of magnitude below Planck energy. Probing quantum gravity requires either vastly more powerful accelerators or indirect tests through cosmology, black holes, and gravitational waves. Black hole information paradox arises from combining quantum mechanics and general relativity. Stephen Hawking showed in 1974 that black holes emit thermal radiation and evaporate. Thermal radiation carries no information about what fell in. Quantum mechanics requires information, conservation. Where does the information go? Proposed solutions include information encoded in Hawking radiation correlations, information stored in black hole remnants, or modifications to quantum mechanics. The firewall paradox suggests observers falling into black holes encounter a wall of high-energy particles at the horizon, contradicting general relativity's prediction of a smooth horizon. Resolving the information paradox may require a quantum theory of gravity. Hawking radiation has never been directly observed. Black hole evaporation timescales are enormous. A solar mass black hole evaporates in 10 to the 67 years, far exceeding the age of the universe. Primordial black holes smaller than 10 to the 15 grams would have evaporated by now. Searches for gamma-ray signatures of evaporating primordial black holes have found none. Constraining their abundance, analog black hole systems in Bose-Einstein condensates and flowing fluids exhibit Hawking-like radiation, supporting the theoretical framework. The measurement problem in quantum mechanics asks what constitutes a measurement. The wave function describes superpositions of states. Measurement yields a single outcome. The Copenhagen interpretation says measurement collapses the wave function. Many worlds. Interpretation says all outcomes occur in branching universes. Decoherence shows that interactions with environment suppress interference, making superpositions unobservable at macroscopic scales. But decoherence does not solve the measurement problem. It explains why we do not see macroscopic superpositions, not why we observe single outcomes. Quantum mechanics works perfectly in practice, but lacks consensus on its interpretation. Reality at the quantum scale defies human intuition. Particles tunnel through barriers they cannot classically cross. Particles interfere with themselves in double-slit experiments. Particles are smeared in space until measured. Heisenberg's uncertainty principle limits simultaneous knowledge of position and momentum. Einstein objected, saying God does not play dice. Bohr replied that Einstein should not tell God what to do. Experiments side with Bohr. Quantum mechanics is reality. Accept it or stay confused. The journey from 17 standard model particles to fractional excitons, 6 flux composite fermions, type 2 Weyl fermions, and 3 component fermions spans less than a century. 1920s quantum mechanics gave Dirac fermions and photons. 1930s Yukawa predicted mesons, Pauli predicted neutrinos, Majorana predicted self-antiparticles. 1940s Feynman, Schwinger, Tominaga built quantum electrodynamics. 1950s, Bardeen, Cooper, Schrieffer explained superconductivity, neutrino beams detected neutrinos, parity violation shocked physics. 1960s, Gell-Mann and Zweig proposed quarks. Higgs, Englert to Sprout, Guralnik, Hagen, Kibble proposed mass mechanism, electroweak theory unified forces. 1970s, asymptotic freedom confirmed quantum chromodynamics, standard model crystallized, anyone's predicted. 1980s, fractional quantum Hall effect found fractional charges, with W and Z bosons discovered, Cooper pairs directly imaged. 1990s, top quark discovered, neutrino oscillations, confirmed neutrino masses, quantum computing algorithms invented. 2000s, Higgs boson discovered, topological insulators found, graphene isolated. 2010s, Weyl fermions observed, quantum supremacy demonstrated, gravitational waves detected. 2020s, fractional excitons discovered, 6 flux composite fermions found. Each particle discovery reveals new questions. Fractional excitons challenge the boson-fermion dichotomy. Are they a new fundamental category or a special case of anyone's? Can they be controlled for quantum computing? Do other materials host similar particles? The Brown team plans to study how fractional excitons interact and whether their behavior can be controlled. 6 flux composite fermions expand the fractional quantum Hall hierarchy. How many flux quanta can electrons capture? Are there 8 flux, 10 flux, higher flux states waiting at lower temperatures and higher fields? Purdue researchers continue probing the periodic table of fractional states. The universe contains particles we have not imagined. 2-dimensional materials, topological phases, and extreme conditions create emergent phenomena beyond standard model predictions. Quantum materials may host particles that cannot exist as elementary particles. The next particle discovery could come from graphene, from twisted bilayers, from fractional quantum Hall systems, from topological superconductors, or from high-energy colliders. The Large Hadron Collider plans high luminosity upgrades through 2040. The Future Circular Collider proposes a 100-kilometer ring, reaching 100 TeV collision energy. These machines will search for supersymmetry, extra dimensions, dark matter production, and deviations from standard model predictions. Quantum particles define reality at the smallest scales. They are the fabric of existence. They are less like billiard balls and more like waves, less like objects and more like possibilities, less like things and more like events. They pop into being when measured. They vanish when ignored. They exist in superposition until forced to choose. They tunnel, interfere, entangle, oscillate. They obey rules that seem absurd until you calculate their consequences and measure them with 15 decimal place precision. The quantum world does not care about intuition. It does not care that you expect particles to be either waves or particles, not both. It does not care that you expect particles to have definite positions, not probability clouds. It does not care that you expect identical particles to be distinguishable, not subject to exchange statistics. The quantum world is what it is: strange, beautiful, precise, real. In January 2025, Brown University researchers published in Nature their observation that fractional excitons occupy a quantum state never before seen. The particle carries no overall charge. It follows unique quantum statistics. It exists only in the fractional quantum Hall regime, a state so fragile that it requires temperatures 100 times colder than outer space and magnetic fields 1 million times stronger than Earth's. The device, 2 graphene layers separated by hexagonal boron nitride, measures micrometers across. Inside it, physics never before observed by humans plays out. Electrons fractionate, charge divides, new particles emerge from collective behavior. The experiment took years to perfect. The analysis required months. The conclusion is unambiguous. A new class of quantum particle exists, not predicted by theory, not imagined by physicists, simply there, waiting in the quantum foam for someone clever enough to look